Okay, let's unpack this. You know how sometimes you think we've already figured out everything there is to figure out about the most fundamental things, like basic arithmetic operations?
Yeah, it's easy to assume that. We have computational methods for things like multiplying numbers or, even matrices that are incredibly optimized. Some go back like
In
decades.
a century.
It feels like there wouldn't be much room left for like truly significant speedups.
Exactly. But then you see research like this. We're diving into some recent work, a paper that just came out, May 2025, plus some related notes. And it looks at speeding up something really fundamental, but also super common, a specific type of matrix multiplication.
That's right. They're focusing specifically on computing a matrix multiplied by its transpose, that XXT product.
So our mission in this deep dive is to really get into this source material. We want to understand this new algorithm they've come up with called RXTX. How does it actually squeeze out more speed from this calculation?
And maybe the most fascinating part, particularly from an academic angle, is the way they found it. The method itself is pretty innovative.
Yeah, that sounds really interesting.
It's a fantastic case study, really. Shows how focusing on these structured problems and using these, well, novel ways to discover algorithms can still give you surprising gains, even for basic stuff.
Speaking of basic stuff, general matrix multiplication, just A times B, that's been a huge topic in computer science forever, hasn't it?
Oh, absolutely foundational, yeah. Optimizing matrix multiplication is one of those like classic quests. You think about Strassen back in 69, Winograd in 68.
Right. They showed you could actually beat the standard sort of schoolbook method, the ON3 way.
Exactly. Got the complexity down to ON to the power of log base 2 of 7. Those ideas, they've shaped algorithm design ever since.
But like you said, XXT isn't just any matrix multiplication. It's X times its own transpose. How does that specific structure make it special, and why does it crop up so much?
Well, that structure, X times X transpose, or you sometimes see XT times X, it's just surprisingly ubiquitous. It pops up constantly across so many different fields.
So where do the sources say we actually see it in action?
Oh, it's kind of everywhere once you start looking. Statistics, data analysis, for sure. It often represents things like a covariance matrix or maybe a Graham matrix.
Okay.
And if you're doing something like linear regression, solving those normal equations often involves calculating XTX, inverse times XTY. And boom, there's that XTX term.
Gotcha. And linking it to, modern computing,
Yeah.
cutting edge stuff.
Yeah, and this is crucial. It gets computed repeatedly in modern deep learning, especially when training large language models, LLMs.
Ah, okay.
The sources specifically point to its use in certain optimization steps, things like the Newton-Schultz step, which you find in optimizers like Nuon, or in update rules for other maybe more complex optimizers like SOAP and Shampoo.
Right. And when you're training these massive models, billions, trillions of parameters, doing these steps over and over.
Millions of times, yeah. So even a tiny percentage improvement on a core piece like XXT computation, it adds up to huge savings. Massive savings in time, in cost.
Okay, so for XXT, just like general matrix multiplication, we're still kind of stuck in that same complexity ballpark, right? Roughly, give or take. The aim isn't a fundamental change in scaling.
No, not changing the big O notation.
It's about improving the constant factor, that number out front, making it just a little bit faster each time you do the operation.
Precisely. For operations you run constantly, at enormous scale, that constant factor is everything. And that's exactly what this new algorithm, RXTX, targets.
Right, RXTX. So what are the big claims? What do they say it achieves?
So RXTX is pitched as this new algorithm, specifically tuned for XXT. And the main claims are pretty compelling. Compared to what was considered the state-of-the-art before, RXTX apparently uses 5% fewer multiplications, asymptotically speaking.
Okay, 5% fewer multiplications.
And just as importantly, 5% fewer total operations. That counts both the multiplications and the additions.
And this isn't just some theoretical thing for infinitely large matrices, right? They're saying it helps for practical sizes, too.
Exactly. They make a point of showing the benefits aren't purely asymptotic. They kick in for smaller matrix sizes, too, which is really important because these recursive algorithms always break down big problems into smaller ones eventually.
Okay. And the researchers?
Dmitry Rybin, Yushun Zhang, and Zhi-Quan. They're from the Chinese University of Hong Kong, Shenzhen.
Got it. So let's dive into the academic meat here. How does RxDX actually work structurally? How does it get that constant factor win?
Okay, the core idea academically is its recursive structure. It's like Strassen in that sense, it's recursive, but it's based on 4 by 4 block matrix multiplication.
4 by 4, interesting. So not the 2 by 2 blocks Strassen uses.
Right, so if you have your big matrix X, you conceptually chop it up into 4 by 4 blocks. The algorithm then tells you how to compute the corresponding 4 by 4 blocks of the result, the XXT matrix, by doing operations on smaller blocks. And that includes making recursive calls to RXTX itself on those smaller N4 size blocks.
Okay, so it's divide and conquer, but tailored. 4 by 4 blocks specifically for this XXT structure. How does that compare mathematically to the previous best method?
So the source identifies the prior state-of-the-art, for real numbers anyway, as an algorithm from Aragoni and others back in 2021. Their approach basically took Strassen's algorithm, the 2 by 2 block 1, and applied it recursively.
Ah, so they use Strassen on the blocks.
Yeah, it effectively turned the structured XXT problem into a set of general matrix multiplications on the smaller 2 by 2 blocks.
Okay, so we're comparing RXTX's 4 by 4 recursion against the old way, which was like recursive Strassen on 2 by 2 blocks. Let's look at those recursive formulas they give. That seems key to the academic difference.
Exactly. Those formulas really capture it. For just the multiplications, the old state-of-the-art, let's call it cos Sn, follows something like Sn equals 4 times Sn2 plus 2 times Mn2, where Mn is just the cost of a general matrix multiply.
Okay, 4 recursive calls, 2 general multiplies.
Right. But RXTX, being based on 4 by 4 blocks, has a different recurrence. Let's call its cost Rn. Its Rn equals 8 times Rn4 plus 26 times Mn4.
Wait a second, let me process that. Rn has 8 recursive calls compared to 4 for Sn, and it needs 26 general matrix multiplications per step, whereas the other one only needed 2. How does that end up using fewer multiplications overall? That seems backwards.
Yeah, it does seem counterintuitive at first glance. But it comes down to the magic of exploiting the XXT structure within that 4 by 4 decomposition.
Yeah.
Even though there are more terms in a recurrence, those 26 Mn4 general multiplies the way they combine, and the coefficients involved mean the overall constant factor multiplying the cost of Mn ends up being smaller as Mn gets large.
Oh, okay.
So asymptotically, the constant for multiplications in RXTX works out to be effectively 2,641 times the cost of general matrix multiplication at that scale, which is about 0.6341.
Okay.
The previous state-of-the-art's constant, derived from that 2Mn2 term essentially, leads to a factor of 23, which is around 0.6666.
I see. So even though the formula looks messier, that 2641 is smaller than 23.
Exactly. That small difference between roughly 0.634 and 0.667, that's where the asymptotic 5% reduction comes from. The paper has figures showing this really clearly. The ratio Rn, Sn dips below 1 and heads towards 95% as n grows.
Fascinating.
Okay.
And what about smaller matrices, where recursion hasn't fully kicked in or the overhead might bite?
Yeah, that's another key point they make. The advantage isn't just theoretical out there for huge n. Even for the base case N4, where you're just doing that fundamental 4 by 4 block calculation without recursion, RXTX uses only 34 multiplications.
Compared to?
Compared to 38 for the previous method applied to a 4 by 4 case. So that's a 10% reduction right at the base level. The speed up is there even for the small building blocks.
Okay, fewer multiplications, that's huge. But computation time is multiplications and additions. Did they tackle the additions too?
They absolutely did. That was another focus. Their initial algebraic scheme for this 4 by 4 block thing actually generated 139 additions per block step, which is quite a lot.
Yeah, sounds like it.
But they put in significant effort to optimize that. They use techniques like finding common subexpressions to compute things once and reuse them. They reference some recent work by Mortensen and Wagner from 2024, which was also about cutting down additions in matrix multiplication.
And they managed to reduce that 139 down to...
They got it all the way down to 100 additions per block step.
Wow, from 139 to 100. That's a big drop in additions. So how does that impact the total operations comparison?
Well, when you factor in those 100 additions along with the 34 multiplications, and you look at the total cost asymptotically, called R plus N for RXTX and S plus N. For the old way, the analysis shows RXTX starts winning, starts being faster overall when the matrix size N hits 256 or larger.
256 by 256. Okay.
Yeah, the figures in the paper show that crossover point really nicely, right around N equals 2 to the power of 8, which is 2 vocal 5.
So it's faster asymptotically for both multiplications and total ops, and the benefits start showing up for matrix sizes that are definitely practical, like 256 squared and up.
Exactly. And they also talk about implementation details, like choosing an optimal cutoff size. That's where you stop the recursion and switch to a standard, maybe hardware-tuned algorithm for the really small subproblems. With those optimal cutoffs, they say RXTX can beat naive multiplication even for n around 32, and it consistently beats the previous recursive Strassen method for n of 256 and above.
Okay, that makes sense. Which leads us to the real world. Theoretical wins are great for academia, but how does it actually run on hardware?
Right. So they did run practical tests on a CPU using pretty large, dense matrices, 6 to 144 by 6 to 144. That's a decent size, relevant for many applications.
And the results were?
The results really back up the theory. RXTX showed a clear speed advantage. On average, it took about 2.524 seconds to compute XXT.
Compared to?
Compared to 2.778 seconds using a standard, highly optimized library routine like a BLAS3 function, doing the same calculation.
Wait, hold on. That's what, nearly a 9% speed up against a standard optimized library for something this basic? That's actually pretty substantial in practice.
It really is significant, yeah. And they didn't just run it once. They ran it 1,000 times, and RXTX came out faster in 990 of those runs.
Wow.
Now, they do add the usual caveats, performance depends on the specific CPU, memory, how exactly you implement it.
Yeah.
That's always true. But the empirical data definitely shows a real-world benefit from this theoretical constant factor improvement.
Okay, so we've got RXTX, proven faster theoretically, shown faster practically for this key XXT job. Now, let's shift to that other big innovation you mentioned. The way they actually found this algorithm, it wasn't just someone having a eureka moment with algebra, right?
That's exactly right.
Yeah.
And this discovery method might actually be the most sort of forward-looking academic contribution here. RXTX wasn't just figured out by human intuition or grinding through algebra manually. It came from combining really cutting-edge machine learning approaches with powerful combinatorial optimization tools.
A hybrid discovery method. Okay, tell us about this pipeline they set up.
You can think of it as playing to the strengths of different computation styles. They call it an RL-guided large neighborhood search, and it incorporates this two-level mixed integer linear programming, or MILP pipeline.
Okay, RL MILP.
Yeah.
Break that down a bit. What do the pieces do?
Okay, maybe an analogy helps. Imagine the machine learning part, the RL agent, is like a really creative brainstormer. It throws out lots of potential puzzle pieces, maybe a bit messy, but lots of ideas.
Okay.
Then the optimization part, the MILP solvers, that's like a super rigorous, incredibly fast logic engine. It takes those pieces and figures out the absolute best, most efficient way to assemble them to solve the puzzle perfectly.
Got it. Creative ML proposes, rigorous optimization selects and refines. So what are the actual steps in their pipeline?
Step 1. A reinforcement learning agent gets involved. Its task is to propose potential rank 1 bilinear products. These are like the fundamental Lego bricks of matrix multiplication algorithms. Think of them as terms formed by multiplying some linear combination of elements from X with some linear combination of elements from X transpose.
So the ML suggests candidate building blocks for the multiplication.
Exactly. It samples potentially useful candidates from a huge space of possibilities. Then, step 2, it hands off to the combinatorial optimization part using these MILP solvers. The first solver, MILP-Perry, takes the candidates the RL agent suggested, and it systematically finds all the linear relationships between these suggested building blocks and the actual target values we need, the elements of the final XXT matrix.
So it figures out how the suggested pieces could combine to make the final answer.
Right. And then step 3, the second MILP solver, MILP-PP, does the really clever bit. It looks at all those possible relationships found by MILP here, and it selects the smallest possible subset of the original candidate products that can still generate all the required elements of XXT correctly.
So that's the optimization step, minimizing the number of products needed, which translates directly to minimizing multiplications.
Precisely. That's how it finds the most efficient combination. And the authors really stress how efficient their particular implementation of this hybrid approach is. They explicitly describe it as a simplification of the alpha tensor RL approach. You might remember alpha tensor from DeepMind. That was a huge deal in using ML for algorithm discovery.
Right. I remember alpha tensor finding new ways to multiply matrices. How is this RXTX method simpler?
Well, they managed to dramatically shrink the search space the RL agent has to deal with. Instead of having the RL agent operate in the incredibly complex tensor space that alpha tensor used, here the RL agent just samples these candidate products first. Then the MILP solvers handle the complex combinatorial task of finding the optimal way to combine them.
Okay, so it divides the labor more effectively.
Kind of, yeah. And the result is a search space that's smaller by a factor of about 1 million, which is just massive. And they also mentioned that the MILP problems they set up are actually rapidly solvable in this context.
1 million times smaller search space. Wow. That makes it much more tractable. Can that 2 by 2 example they mentioned help make this concrete?
Absolutely. It's a great simple illustration. For just a tiny 2 by 2 matrix X, the result XXT only has 3 unique elements you need to figure out.
Okay.
So the process would be the RL agent samples some potential products, those building blocks. Then mil-P figures out how linear combinations of those products could form those 3 target elements. And finally, mil-B finds the minimum set of products needed to actually generate those 3 elements. It shows how the system effectively searches through algebraic identities to find the most efficient one, like the one using 34 multiplications for the NeVo4 case, by optimizing combinations.
That hybrid approach, ML exploring possibilities, optimization, rigorously selecting the best that feels genuinely powerful, like a new way to do algorithmic research.
It really does. It feels like a significant step forward in the process of discovering algorithms, not just the algorithms themselves.
So let's pull this all together. What's the main takeaway from this deep dive into RXTX?
Well, first, RXTX is a real practical improvement. It gives measurable speedups for computing XXT, which we've seen is fundamental and super important, especially now with things like LLM training. That 5% or even 9% in practice on something done so often, it translates to potentially huge savings in compute time and energy.
And it really drives home that academic point, doesn't it? That specializing algorithms for specific structures, like XXT, is crucial. You can't just rely on the general matrix multiplication algorithm. That constant factor really, really matters in the real world.
Exactly. It's not just a footnote in a complexity formula. It's where the practical games live.
And maybe the biggest splash, academically speaking, is the discovery method itself. This work just shines a spotlight on how powerful these hybrid techniques can be, combining ML's pattern-finding ability with the strict logic and optimization power of solvers. It's not just for analyzing data anymore. It's becoming a tool to invent completely new, more efficient ways to compute things.
Yeah, finding fundamentally new algorithms for basic computing tasks this way.
It's kind of wild, isn't it? Thinking we're still finding better ways to do something as old as multiplication.
It is wild, but it also makes total sense, right?
Yeah.
With the pressure for efficiency in AI and big data, every cycle counts. Those small optimizations have massive ripple effects.
Absolutely. So here's a final thought then, something for you, the listener, to maybe mull over after this deep dive. If techniques like this, combining machine learning intuition with optimization rigor, can find a faster way to do matrix multiplication, a cornerstone of computing, where else could they work? What other fundamental operations, maybe in math or science or engineering, might have hidden efficiencies just waiting for this kind of hybrid discovery approach to uncover them? The potential seems pretty vast.